Okay, so why don't we get started? So the past 6 lectures, I've been telling you how great the standard model is, how we know so much, it's so wonderful, everything is great. And in this lecture, in the next lecture, I'll tell you about the things that we don't know and the fact that we really are missing some basic pieces to that. So it'll be a little different. Okay, so just to remind you about last week, we were really building out for many weeks to last week. So a big theme of these lectures is the fact that these basic principles of quantum mechanics and relativity are really forcing us into the types of theory that we're able to have, the types of consistent theory that we're able to have. And it's incredibly constraining, and in fact, that is exactly what we see. So what we see corresponds to those constraints. And one of the big lessons was that it was really hard to have masses for these particles. Okay, that was in violation of a lot of the basic inputs. But there was a way out. You could add this other field. It kind of looked very ad hoc at first, but you were able to at least escape the get out of the constraints imposed by these basic principles. But doing this had one other prediction, that there should be another particle in the theory. Okay, and it wasn't just a vague prediction that there should be another particle. There was a particle that was predicted with very specific properties, and that was discovered. Okay, so this, and we went through all of this last week. So this was really a big achievement for all of humanity, I think. But it was really not so much discovering this particle was such a big thing, but it was really confirming this picture that by adding this other field, and that's how you give particles mass. Okay, so this happened in 2012. Since then, there's been a whole program to measure the properties of this new particle, and we went into that last week as well. And so we had significant improvement in analysis sensitivities and in the amount of data that we've collected. And all of this agrees within the picture. Okay, and so we've made measurements in many things at sort of the 20% level, and things are in agreement with this basic principle. So it really does look, or basic prediction. So it really does look like the way that the particles have mass in the theory is due to this Higgs mechanism, or this idea that you add this other field with this potential. We've also looked for this new particle behaving in ways that are not predicted, and we haven't seen any sign of that yet. Okay, so this was the slide that I showed in the first lecture. This was sort of outlining the big picture of where we were going, and I talked about the extremes that we had to go to find this particle, and that left us with a number of questions. And so many of these we've now answered. So why to look for the Higgs boson in the first place? We've answered that in sort of a couple different ways. There's the general way that this is really the frontier of this program to unify everything, the scientific descriptions of everything, and that was really the next obvious step. So that was one reason to do it. Another more advanced or deeper reason, or more technical reason within the field is you're interested in this Higgs boson because it can confirm that this Higgs field picture is accurate. So that was another big reason to look for it. And then we answered it at a different level again or a more general version of this question: why should governments support this type of research? And you saw that really clearly, I think, with Jamie's lecture. So that question I think we've answered, and we'll answer more. There's even deeper answers to this that we'll get to later. Okay, so what is the Higgs boson? That we've also addressed. It's an excitation or a sound wave in this Higgs field, and the Higgs field is a big deal because that allows us to have mass. And then why do we need to go to such extremes to find it? So why do we need all of this stuff? And we talked about last week. You saw that because the Higgs couples so weakly to particles that we have lying around, the particles we have lying around have low masses. That means that Higgs is even harder to find than the other particles with similar mass. So we have to produce it through these second-order diagrams. Okay, so that leaves this last question: are we done now that we found it? And this will be the focus of the last two lectures. Okay, so this is again now highlighting problems with the standard model. Okay, so in this business, our aims are really big, right? So we want to describe everything around us, and this is sort of a cartoon of everything around us. So this is all of the length scales that we know about. So on one end is the observable universe. Okay, so this is the biggest possible distances that we can see. This is, in the units, in the good units, is 10 to the 41 inverse GeV, but that's about 10 to the 25 meters. And this is something that's just set by the overall speed limit of light and the age of the universe. Okay, so the universe has some finite age, and so the upper limit, the speed limit, sets the distance of how far we can see back in time. So that's on one end. On the other end is a length scale that we've also seen already. This we saw in lecture 4. This is related to this Newton's constant. So this is the constant associated with the force of gravity. That has a scale that has a length scale associated with it, and we saw it's incredibly tiny. So that's 10 to the minus 20 GeV, or 10 to the minus 36 meters. And as we'll see, we think everything is within these two limits. Okay, so right in the middle, and this, I should say, this is also, you'll see this is a logarithmic scale here. So within, sort of right in the middle is atoms. Okay, so those are 10 to the minus 11 meters. This is a length scale that we actually worked out here. Again, this is set by just the fundamental parameters. And then there's other ones that we've worked out. Okay, so there's animals and planets. You can see there where they are. Those are also ones that we talked about in this lecture series. But there's other ones. If you put sort of everything around us, you can sort of see where it lies. And it's interesting that we have this huge range, and it's fairly evenly populated with stuff. So there's galaxies not so far, not so much smaller than the observable universe. Then you hit solar systems, stars, planets. There's other things that could have put in here as well. So this is sort of what we're after, what we expect to be able to explain. Now, from the experimental side, so if you ask, which of these length scales have we actually probed directly, that's shown here. So we, from the sizes of the observable universe down to within the nuclei and even within protons and neutrons, this has all been directly probed experimentally already. And the LHC, of course, is the frontier of this program, and so it's down here. But this upper bit is unexplored, so we haven't been there, and we don't really know what happens. So this is from the experimental side. You can also ask about the theoretical side. And so, of course, we have the standard model, and this is the standard model before the Higgs discovery. Okay, so before we understood mechanism of masses, and it explains essentially all of this. There's some questions about here that I'll come back to, but this essentially explains all of these length scales up until right where the LHC was going. Okay, and so at that point, the theory itself just broke down, and we talked about this. This is this failure of the scattering of W particles. So these omega particles, where you would get probabilities that were above 1, which were obviously nonsensical, and that happened right at about 1 TeV. Okay, and that's without the Higgs. Now, of course, one of the big things that the Higgs did was solve this problem and made sense of these scatterings. So now the standard model after the Higgs discovery now looks like this. We understand everything up to this point, and in principle, the theory also works all the way up to here. Okay, so this is another reason why the discovery of the Higgs was such a big deal. Right? Before, we had a theory that we knew was going to break down right around the corner, and that so we were before the LHC turned on, we were very close to that point. Now we have a theory that, in principle, is can be extrapolated to exponentially higher energies. Okay, and I think this is the first time actually ever that we've been in this situation. If you look in the history, we've always been in a place where we knew that there was something missing, and the piece that was missing was not so far away. It was, you build another collider, you've got a factor 10 in energy scale, you would see that. Now we're not in that situation. Okay, so it's very different.
Can I interject one thing? Your observable universe, are you using 93 billion light years, and not just 13.87?
So I'm using 10 billion years times the speed of light.
You're using what?
10 billion years, so like about 13.7 times the speed of light.
Because all the astrophysicists agree it's 93 billion light years. I mean, it's like 4 times.
Yeah, and I should say this is all within the squiggle.
But the standard model doesn't explain the size of the observable universe.
Well,
unless you
yeah. So maybe we'll come to those. We'll come to that.
Okay. Whatever.
Okay, so this is one of the reasons why the Higgs was such a big deal. Okay, but in between these scales, as I said, there's really this diverse length scales with a lot of rich structure, sort of within this. And my claim is that all of these intermediate scales are really set directly by basic fundamental principles and basic fundamental parameters. And we've actually seen explicitly examples of these. So we saw that for the atoms, for planets, and for animals, that these are really dictated by fundamental length scales within the theory. So if we really want to understand all of this, it's enough to just understand the fundamental length scales. So that's what we'll focus on here. So here are the fundamental length scale. So it's this sort of same cartoon, but only the fundamental one. So we think this observable universe is fundamental, right? It's just set by the upper speed limit. This lower scale that's set by gravity is referred to as the Planck scale, and that's one that appears directly in the theory. There's another one that we haven't really talked about explicitly in this lecture. It's actually come up a number of times, and this is that we refer to as the weak scale. So this is at 10 to the minus 19 meters. And the weak scale comes about basically because it's directly related to the Higgs particle and the weak force. So you can think of it as it's the scale that's associated with the fundamental particle masses. So like the mass of the W and the Z are at this weak scale. It's also, another way to think about it is it's the mass scale that's associated with interactions with this Higgs condensate. So we have this cartoon of a particle coming along that has mass, and it interacts with this Higgs condensate, and it flips its spin. That was the whole point of this Higgs condensate. And this weak scale is the scale that says how often this happens. Okay, so it dictates the time or the distance between these interactions. And so it's an input to the theory, and it's also technically it's associated with the shape of the Higgs potential. It has this funny double minimum shape, and one of the parameters is directly this weak scale. Okay, and it's also another way of thinking about it is it's really also the first time it's at this distance scale that all the different fundamental forces start looking alike. Right? We said that we have these four forces in nature that seem very different, but at small scales we have found that they operate under the same mathematical structure, and it's at this weak scale that you first start really observing that. Okay, so the LHC now is exciting for many reasons. It's exciting because it's the frontier of this region where we're probing experimentally. So it would be exciting no matter what, but it's doubly exciting because it's also right at this fundamental length scale. So this was a length scale that has been known about since the 60s or even before that. Fermi, someone that really understood this deeply, and now it's the first time that we're able to actually go there experimentally. So it's another reason why this time is so exciting. Okay, so this is all. I'll call this the Hubble scale. There's a scientist that's associated with this. But you should think of this as the size of the universe. Okay, so just a couple of things to note about this scale. There's a really large range here, right? So it's about, I think, 61 orders of magnitude. It's large, but it's not infinite. Okay, it's not. At least the scales we know about aren't arbitrarily far apart. And my claim is that everything we know and we actually can know or can possibly know fits within this range. And that's what we'll go over here. So this upper bound is just set by the finite speed limit, okay, and the age of the universe. Now this will slowly get bigger as the age of the universe gets bigger, but it's not. For our purposes, we think about it as being fixed. And so I'll talk about the lower bound next, but this is also believed to really be a hard limit. So we don't think that we can go below that. And so all the problems associated with the standard model that we'll talk about, all the deep mysteries, are really connected to each of these fundamental scales. Okay, and that's really what the whole. So this is kind of like the outline of today's lecture. Is we'll talk about the mysteries associated with each of these. And another thing that I should have said earlier is, we've made such progress in this theory by just taking these principles of space-time and quantum mechanics combining them, and that's restricted the way things could possibly be. And it's exactly these things taken to the next level that give problems. So all of these problems associated with these scales are a direct result of the same things that worked so well in the past. And so that's why it's so interesting. Okay, we'll start first with the problem associated with the Planck scale, or really this lower bound in the graph before. Okay, and so I want to talk about this by going back to something that we talked about in lecture 4, the relative strength of gravity with respect to the other interactions. So we saw the electromagnetic interaction, between two protons, say, separated by a distance r. That was related. We did this dimensional analysis and convinced ourselves that this coefficient in the energy or in the force is just a pure number. It's just this number it's alpha, and that's about 1 over 137. And for gravity, that wasn't the case. There was something different that happened because you have the masses in this inverse square law, and they have a dimension. So the coupling that was associated with gravity that would be analogous is a dimension full number. Okay, and it's this incredibly small number. This is directly the Planck length, or that's the Planck length that we talked about before. This is this 10 to the minus 20 g number. And so so it's really the combination of this fundamental constant and the mass of the things that is the dimensionless object. So now let's talk about the relative strength of the gravity versus electromagnetism. So if we think when the distances are large, okay, when these things are well separated from each other, then the relative strength of these forces is just set by the strength of this interaction, that's alpha, and the product of this dimension full number with the masses of the things that you're comparing to. And so if we take proton masses, this is a tiny number. So it's independent of distance. Right? The distance, the functional form of the distance is inverse square in both of these cases. So you just get some really tiny number that's independent of how far apart these things are. And this number is like 10 to the minus 37. But however, if you go to smaller distances, because this is a dimensional parameter, ultimately, what's happening is the force of gravity increases. Okay? And the way to think about that is, as we would bring these protons closer together, because of the uncertainty principle, we have to put in energy to keep them, to hold them small radius. Right? So there would be an uncertainty in this distance. If that distance was really small, there would have to be a large uncertainty in their momentum or of their energy. And so the actual energy that we have to put into the system to keep them close together gets big when you're at small distances. Okay, now that energy, we know E equals mc squared, so that energy also feels the gravitational interaction. So once you get to distances that are smaller than 1 over the proton mass, the dominant form of energy is not in the mass of these particles, but it's in the amount of energy that you have to put in to just keep them close to one another. So what happens is at small distance scales, you're actually putting in so much energy to keep these particles here that that's the biggest piece, and now gravity starts to get much stronger. Okay, so that the energy that you're keeping in here goes into this mass that gravity needs. So long distances, gravity is totally irrelevant, and it's also unchanging. But at very small distances, the force of gravity, just by the uncertainty principle, so one of these basic consequences of quantum mechanics, gets stronger, and ultimately it becomes the biggest force at very small distances. Okay, and that's what I say here. So at short distances, so comparable to the Planck length, this interaction dominates. And so another way of thinking of this Planck length is this is the scale at which gravity becomes important. Okay, where gravity becomes strong. Okay, so now we could do a thought experiment of here are the fundamental scales. This is where we've directly probed. What would it take to probe the smaller distances? Let's say we wanted to really understand gravity and go down here. So we talked about, by the uncertainty principle, we have to build colliders to do this. We have to put in very high energy to probe these small distances. Okay, so we know how to do this. We can just build bigger versions of the LHC, and it costs a lot more money, and have these colliders go to much higher energies, and that would get us. There's no problem extending the scale. So this comes back to the question that you've been asking multiple times. So you'll get the answer now. So eventually, everything works, right? If we build a bigger collider, we can access all the energies. But eventually we get to the point where gravitational interaction dominates. So now we just totally ignore gravity and we go to smaller and smaller distances. Eventually we couldn't do that. Eventually we'd have to take gravity into account, but that's fine. We can take gravity into account and still go to smaller and smaller distances. But then something new happens. So eventually we get to the point where there's really something that's qualitatively different. And I'll talk about that in the next slide. So we create black holes. Okay, so this is one of the important things with gravity, is that at some point you can put so much energy. If you remember, we're applying these things. We're putting all this energy in a very small region, and that's how we're probing these small distances. Eventually, you put so much energy into such small a region that you create a black hole. Okay, so that is, you create something that has so much energy that's localized that things that were moving even at the speed of light couldn't escape from. Okay, and that's, we normally think of black holes as astronomical objects, but if the energies are really, really large, they can also be produced microscopically. So we can estimate. So now, after the fourth lecture, we're all pros at just doing this rough estimation for when things happen. So we'll work through that here. Here's the energies. Okay, so this is the energy associated with gravity. So it has this scale. This is like the mass squared would be of a planet, but we can think of this as the energy that we're putting in to probe the small distances, and this is the distance at which we're probing. And you make a black hole when the amount of gravitational energy is roughly equal to the kinetic energy that something moving at the speed of light would have. Okay, so this is how you would get it for like the estimating of the planetary size black hole. And as I just said, so the dominant piece of this mass of the mass is associated with the energy that the collider is providing. Okay, and that energy just by the basic uncertainty principle is about 1 over the distance that we're probing. So we can stick this into these equations. Okay, and you get power 3 here, power 1 there. C, of course, is 1 in the natural units. And this tells you that at the radius that's like square root of g Newton, or at the Planck length, so that was the low boundary, this is the distance scale that you start producing black holes. Okay, so it's incredibly far from where we are now. But nonetheless, this was what would happen. Okay, so this program to keep exploring this region would work until gravity becomes dominant. Then once we get to this region, we start making a black hole. Okay, now of course the whole point one of the things of black holes is that nothing can come out. Right, so any information about what's happening within the black hole or at smaller distances is inaccessible to us. Right, we can't. There's no way you can get. Things can't move faster than the upper limit, and things moving at the upper limit can't escape. That's why that black holes are black. So we can't tell what's happening at the Planck length. Okay, because the information just doesn't get out. So you can say, okay, well, I know what I'll do. I'll make a bigger collider. I'll make it 10 times bigger. Okay, so if you do that, then what you do is you make a bigger black hole. Okay, and you still can't get information. So this is the point where it doesn't make any sense to build a bigger collider. Now, of course, this is tremendously far from where we are, but nonetheless, we think this is a real battle. Okay, so what this is saying is that these basic physical principles are saying that there's nothing that we can do, even in principle. Okay, even if we had unlimited amounts of money, time, and energy in grad students, could we go to these smaller scales? Okay, so we can't get information about these in principle. And every time this has happened in physics, every time that the physics is saying, in principle, this is something that you can't have access to, that means that something doesn't exist. Okay, so we've seen this many times. So like in quantum mechanics, tells us that just even in principle, you can't know an object's position and momentum arbitrarily precisely. And now we can see that that's really just saying that doesn't exist. The notion of position and momentum together at arbitrarily small distance does not exist. And we saw that with relativity as well, that different people can differ on the time something happens. So the absolute time is something that just fundamentally doesn't exist. And it's the same thing that's happening here. Right? Physics is really telling us that there's nothing that you can do to make sense of smaller distances than this Planck scale. And so that's a big hint that these smaller distances are actually don't exist. Okay, so we really think that this is a lower limit, and I should say, so a lot of this stuff, this is, I would say, 99% of the people in this business agree with, but we're now in a murkier territory than we were with the previous lectures. But this, I think, is fairly solid. So, the consensus is that there's really a lower limit to space-time. Okay, so our notion of distances at these really small scales is breaking down, okay, near the Planck length. And so it's not really clear what replaces it now. We have a lot of ideas, and this is actually a major issue. Okay, it's experimentally it's not that big of a deal because it's so far away from where we are now that it's not likely. We can certainly act as if space-time exists now, but we need to understand these very short distance scales for a number of conceptual problems. So, understanding what happened in the early universe. So really right after the Big Bang, there you have length scales that would be at the Planck length. You'd like to understand how the universe is evolving on those scales. And we don't know, we clearly don't understand that. A lot of the details of black holes, so what's happening with black holes requires an understanding at this fundamental length scale. So understanding what replaces space-time at these lower distances is something that you really need for understanding these problems. That's also why black holes are so interesting, is because we think that they can perhaps tell us about how to replace space-time at these distant scales. And then the other thing that I think is a more philosophical thing is that the whole point of physics is about what happens in space-time, right? We have these diagrams, and that's the whole point of what we're doing. And if space-time doesn't exist, then we have to ask what should physics even be about at these low distances. So this is really a major issue, and one that people are actively working on, but we don't really have, there's not a clear solution. We have some hints that something is needed, okay? And so there's a lot of progress in this, and that actually what replaces space-time is quite dramatic. And I can talk more about this maybe afterwards if people are interested. But yeah, so we have toy models where we know exactly what's happening. It's really that once you get to the lowest limits, there's no notion of the inside of things. And I can talk. I'm not a total expert in that, but I can talk about that. So it's really, we think that there's hints that it's a dramatic change that's needed at low energy scales or low distance scales. Okay, so that's the first problem. That's the problem associated with this fundamental length scale. Now I'll talk about the problems associated with the other fundamental scales, the weak scale and the Hubble scale. So the problems are actually closely related. I mean, they're really like cousins of each other, and they all come down to this issue of vacuum fluctuations. Okay, so this is again something that was really just forced on us by combining quantum mechanics and relativity. And so this is just a reminder from slide 2 what this is about. So we had this notion that we had to have antiparticles, that they had to exist in the theory. And then this meant that if you had antiparticles, that there was nothing that would prevent you from creating pairs of particle and antiparticle. So if you put in enough energy that, because it's quantum mechanics, there's nothing would be violated. So you're conserving charge, you're conserving all the relevant all the relevant quantities that you could just produce, pairs of matter and antimatter out of the vacuum. Okay, and this is what's referred to as vacuum fluctuations. And of course, these have been a big star of this lecture series. So these things are real. I mean, at first they say maybe they're not real. Maybe they don't have an effect. It's something that's possible in principle. But they are real. Okay, they've been shown to be real, and they're incredibly important for things like these detailed calculations. So I said, we're able to predict how much of a magnet an electron is, and we're also able to measure it incredibly accurately. And the whole prediction of, to get this agreement depends critically on the effects from these vacuum fluctuations that we saw, I think, in lecture 3. So also, we saw this in just predicting the fact that there should be a particle in the theory. So we saw, before the top quark was discovered, you could infer that there had to be a top quark by something that was just like a vacuum fluctuation that modified the Z boson mass. And that's what we saw here. So this is before the top quark was discovered in 95. Before that, you had this prediction from assuming that these vacuum fluctuations were real. you can predict that there should be a top quark, and this is what the mass should be, and it was exactly agrees with what we found. Okay, and then of course we saw this with the Higgs. We knew that we had a limit on the Higgs mass coming from these vacuum fluctuation diagrams that look like this, and what we saw is consistent with this prediction. So vacuum fluctuations are real, and they're a reason that the theory is so successful. Okay, so there's something that we have to take seriously. Okay, and so one of the interesting things that comes in, again, just with quantum mechanics and these vacuum fluctuations, is that the vacuum has energy. There's energy associated with it. So this is something that we saw in the second lecture, that if you just have a system that's like a ball hanging from a string that can swing back and forth, that classically the lowest amount of energy is zero, so it can just be sitting here not moving, so it has zero energy. But with quantum mechanics, you have this uncertainty principle that kicked in, and it could be localized here. So there was always some fundamental jitter, and that jitter is associated with the frequency with which this thing can oscillate. So there's really a minimal non-zero energy. Okay, so it's exactly this kind of thing that allows us to where the vacuum energy comes from. So it's a fact that even empty space has these quantum fluctuations, and they have this frequency or frequency associated with them that sets the minimum energy. Okay, so we can estimate how much energy, or the energy density, so how much energy per unit volume there is to empty space. Okay, and so we'll do this again with the simple dimensional analysis that we talked about. So if we take a box, just a box of empty space that has some length L to it, again, in empty space, we can try to get just a rough feeling for how much energy we think there should be there, how much energy density, or energy per unit volume of this box. So this one's easy. So the energy density is usually written as lambda, so that's what that means. It's an upside down V. So this energy density has units of energy per volume, right? And the volume is easy. That's just the cube of the length. Okay, there's only one scale in this thing. There's only one thing here. It's the box. So there's the volume goes like L cubed, and energy to get the correct unit has to go like 1 over length. Okay, so this total energy density goes like 1 over the length of this box to the fourth. Okay, so this is interesting because now if we make a smaller box, okay, this lambda gets much bigger, and it grows with the fourth part. And so this seems problematic because now I can just, if I want to calculate how much energy is here, I calculate this box, I get some number. Now I get to go to a smaller box, I get an even bigger number. So it looks like the amount is infinite, right? Because I can keep going to smaller and smaller boxes. The energy density keeps getting bigger and bigger. So it looks like I have infinite energy in the vacuum. Now, of course, we just said that we can't do this arbitrarily small because at some point we think there's a fundamental limit. And so certainly when we get to the Planck length, this naive calculation doesn't work, right? Because we don't know if this length is even. We can even go to smaller distances than this. So it certainly doesn't make sense to calculate energy smaller than this Planck length, right? But we think it looks, as we approach this Planck length, the space-time exists, and we're not making black holes, so there's no problem. So we can do the calculation with the cutoff, is the term in the literature. So we reach a point of the calculation which we don't trust anymore, and that's where we stop doing it. And so very naively, if the only problem is at the Planck scale with black holes, we expect this cutoff to be at the Planck length. So the vacuum of the energy, or the energy density of the vacuum, should be something that's roughly 1 over the Planck length. Now, of course, this can change depending on what's happening at the Planck, beyond the Planck length, but it should be at least this big. Okay, so this turns out to be a problem. Okay, and I'll explain why that is. So this is there's a problem that has a name associated with it. It's called the cosmological constant problem. Lambda is often called the cosmological constant. Okay, so without gravity, if gravity is not important, constant energies can totally be ignored. Okay, the only thing that matters is distance, or is differences of energies. Okay, so this vacuum energy density is just some overall constant that we can subtract off. Okay, so it's totally irrelevant. With gravity, and of course we think we need gravity at big distance scales or even small distance scales. this constant energy warps space-time. Okay, so if you have, so this density is uniform in space, right? It's everywhere you have the same density. If we had inhomogeneities or places where you had bigger energy, smaller energy, then that would clump. So that's how we could get planets and galaxies. But with this, it's really uniform. And so if you have this constant energy or constant mass, what it does, its main effect is to govern how the universe itself changes. Okay, and so again, we could work this out easily if there was more time. But basically, uniform matter and energy controls either the size of the universe or the expansion rate of the universe. So how fast it's expanding, or the size if it's not expanding. And so we'll just take the expansion because that's our universe is actually expanding. So we'll use that scenario. So like the doubling size of the universe. So how much time it takes for the universe to double in size is related to how much energy density you have. Okay, so if you have an energy density, that can cause the universe to expand, and this doubling rate is given by something that goes like the Planck length squared times this energy density. Okay, so if we take this naive cutoff of, we say we understand everything up to the Planck scale, that means this number is like 1 over the Planck scale to the 4th. Okay, if you put that number in there, this gives a doubling time of the universe of 10 to the minus 43 seconds. Okay, and this is bad, right? This would be bad for atoms, planets, people. Things would be, the universe would be exploding essentially faster than things could form, right? So there would be nothing. Okay, so obviously this is saying that this cutoff, that this is not the right cutoff to use. And so I said that, there's this. If we think of the cartoon in the beginning, we've explored places all the way down to about the weak scale. So maybe we should put in the weak scale for the cutoff, because we actually haven't really been to places distance scale smaller than the weak scale. So if you put the cutoff at conservatively, so this is below factor 10 below the weak scale, this gives a doubling time of the universe of 10 nanoseconds. Okay, and this is also not good. So it's certainly bad for planets, people. I think it would also be bad for atoms. I haven't convinced myself that, but it's certainly not. It's totally inconsistent with us being here in this lecture today. So it's a problem, right? And now we've actually, so the universe, as I said, the universe is expanding. We've measured it recently, and it's expanding at a rate. So it doubles at like 10 to the 10 billion years. Okay, so like the age of the universe. And this, if we took this estimate seriously, this would require a cutoff that's at the 10 micron level. So at distance scales that we've definitely been to before, it's saying this naive calculation doesn't make sense. Okay, so clearly there's something wrong with this picture, and the only thing that we're putting in here is the basic quantum mechanics, relativity. It's the thing that made us so successful to begin with. So clearly there's something wrong with what we're doing. Okay, so now I said how great the standard model is and how it can predict everything down to the weak scale. But this, we just saw, is suggesting that there's a problem with the 10 micron level. And so how does the theory actually cope with this problem in practice? So I'll tell you what we actually do in practice. It turns out that it's not a problem to any of the calculations that we do. So here's what we do. We say that there is this energy density of the universe. Okay, it is present, and it behaves just like we talked about. But there's two pieces. There's the piece that comes from these vacuum fluctuations. Okay, that's the piece that we just talked about. But then there's this overall, remember I said that energy is, you can add an overall offset to it. So there's some overall offset in the theory as well. That's like the classical term. This would be an input to the theory. So some parameter that we would say that the theory has. So we say that there's these two pieces. Okay, this is the one that we just talked about. And this is just some constant, so it's just some number, right? So we do this calculation. Okay, we calculated this number. We said it should be about the Planck 1 over the Planck weight to the 4th. Okay, so this is the number shown in units of Planck length. So it's like 3. Okay, for example. And let's say we were really good and we calculated this to 120 decimal places. So it's like 3 when it has all these things, all these numbers. So we say this is the quantum mechanical version. And then there's a classical one that we add to it that just happens to be -3, and it agrees to 120 digits, okay? And then at the 121st digit, it disagrees, right? Now, if you choose this parameter like this, then everything's fine, right? Then the only place it makes the overall energy density consistent with what we observed, and it doesn't affect any of the other calculations. So this is really what we do in the theory now. This is called fine-tuning, okay, because we have to fine-tune this input parameter to 120 digits, and it's clearly wrong. I mean, it's clearly telling us that we're missing something. No one is really happy with this. But it's associated with, you can think of it as this problem associated with the distance between these two length scales. So why do we have to do this fine-tuning is analogous to saying, why is the universe so big? Well, why is the thing that we observe so different from what we expect, naively based on this Planck scale? Our answer to this now is because there's this other parameter that agrees with the calculation by 120 decimal places. So it's, no one's happy with this. Okay, so that was the problem associated with the largest scale. The problem associated with the weak scale is very closely related. It's the exact same physics. It's these energy, well, you'll see it here. So we have these vacuum fluctuations. Okay, they also are problematic for the Higgs. So I'll talk about the Higgs particle first, then we'll talk about the Higgs field next. So you can ask what these vacuum fluctuations do to the Higgs mass. So we said that there are corrections. So there's a Higgs mass term, and there can be corrections from these loop diagrams like this, which are they're exactly vacuum fluctuations. So if we would do this calculation, it would turn out that the correction to the Higgs mass is dominated by this diagram. And you shouldn't be surprised because the top is the heaviest particle in the theory, so this number is the biggest. But if you do the calculation, this is telling you that this correction is biggest and biggest when the amount of energy that the top has when it fluctuates is the biggest. Okay? Or another way of saying that, this diagram goes like the cutoff squared. Okay? So if naively you would get something that's like the Planck scale, okay, when you do this correction. So now this is directly related to the Higgs mass. So that's telling us that the Higgs mass, if these quantum effects are real, and they're viable down to the Planck scale, the Higgs mass should be something like 10 to the 20 GeV. And which of course it's not, right? It's 125 GeV. So what do we do here? Well, it's the same thing. We say, okay, yeah, they're really, this is a correction, okay, and so the Higgs mass that we measure is this number, okay, which should be naively the Planck scale squared, and so maybe it's 2 with 60 digits. Okay, and then we say, but there's another parameter of the theory that's lying around. That's the classical version. It's the exact same thing that we do for the other problem. So there's another parameter to the theory. This one happens to be -2.56, blah, 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 agreeing exactly with this to 60 digits. Okay, so again, totally implausible. So this is saying that we would estimate these corrections for the Higgs to be unreasonably large. And it's actually worse than that, because if there's something, as we'll see, we really think this is an instability to the Higgs mass. So if there's a new heavy particle in the theory that's beyond where we fit now, we would expect there to be another diagram like this. Okay, but this has the biggest mass, right? Because if this mass is heavier than the weak scale, we would expect a diagram like this to be present. And so there should be a correction to the Higgs mass that goes like the mass of this particle. Okay, so it's very strange that this problem is not just associated with the weak scale. It could be anything if there's any other new physics beyond where we've been, we would expect pieces like this. Okay, so for this, there's always an analogy that I use here. It's kind of like walking into a room and seeing a pencil just standing on its end. Okay, so seeing something that looks like this, right? And for the Higgs, there's actually two ways of thinking about it. So first, let's consider that there's no such thing as atoms, or the only active degrees of freedom are the pencil and the table. Okay, so there's no sound waves in the room. There's no molecular vibrations or anything. If we saw this, it would still be very strange, right? It would be very bizarre. it's consistent with physics. It's not violating any of the basic physical principles. You know, the forces are balanced here. But without these small scale effects like vibrations or temperature, this would be very bizarre, but it would be stable, and you would suggest some fine tuning, right? Like someone really spent a long time getting this pencil to stand on its tip, and they didn't touch it. But now, if we turn on this small scale physics, so the fact that there's sound waves in the room, there's vibrations at the table, that would rapidly, even if you got it to this place, it would rapidly make this be unstable. Okay, so any kind of vibrations or air molecules, even just atomic motion, would quickly lead this pencil to fall over. So if you saw this, and we know that these things are there, right? We know that these things exist. So if you walked into a room and you saw this, it really suggests an active mechanism, right? It suggests that there's some string hanging from the ceiling that's holding it up, or maybe there's some glue or something down here keeping it in place. But you need something to protect this stability. Okay, and this is exactly like the Higgs. So the Higgs mass wants to fall, it should be on this table, right? But we see it in a very unusual, unstable place. So if there was nothing else in the standard model, it would be like the scenario with the pencil, without vibrations. It would still be very strange, but it would be stable. As we'll talk about next week, we expect there to be other things in the standard model, and that is more like this situation. So we really expect there needs to be an active mechanism to protect the Higgs mass from falling over. Okay, and we'll talk about that. Next week. And another thing I should say is this effect is particular to the spin zero particle. I said a couple times that one of the weird things about the Higgs mechanism is it predicted a spin zero particle, and spin zero particles have this fact that they're sensitive to what's happening at the cutoff scale. Okay, so the other particles aren't. Maybe I'll skip this here. I can talk about this if people are interested. But these other particles are actually protected by certain symmetries in the theory, so they can't get very large corrections. Okay, so that's how these vacuum fluctuations impact the Higgs. Another way of saying the exact same problem is talking about what they do to the Higgs field itself, so the Higgs condensate. So this is really the same problem, it's just a different way of phrasing it. But so you can perform a similar estimate. So just like we looked at this vacuum energy density of the universe, you can do the exact same estimate for at what scale the interaction with the condensate. Okay, so I said that. So that's what I say here. So I said that before, you can think of the weak scale as like saying when. How much distance or time there is between when particles interact with this Higgs condensate. But you can estimate that. You can estimate what that should be naively. And if you do that, you should get something that goes like 1 over the cutoff scale. So this thing should be, this thing wants to interact at the smallest distances it can. Okay, it's the exact same arguments. Okay, so again, naively, we expect this cutoff scale to be the Planck length because we think physics makes sense down to that point. If we put in this Planck length scale, that means that the distance between when particles interact with the Higgs field is like 10 to the minus 20 GeV, okay, where that's 10 to the minus 36 meters. And of course, we've now observed this, and the measured scale is actually more like 10 to the minus 19 meters. So again, very different answer from what we naively expect. This is also bad. If they interacted with this cutoff at this distance scale, it would be very bad for us. And so what would happen is, if the cutoff is the Planck length, people out of this planet, they would all be black holes, right? They would have so much mass. The amount of mass you have is directly related to how often you're interacting here. If they interacted with this distance scale, they would have so much mass that they would all be black holes. So again, obviously not what we observe. And the way to see that is, we did this naive calculation of what the force of gravity is relative to E and M. So this ratio is roughly the gravitational constant, that's the Planck length squared, times the mass of this system. And the mass is just directly, before this was like the proton mass squared. But if this was the cutoff, it would just be the cutoff squared. And so if the cutoff is really the Planck length, we expect this ratio to be 1. This is the Planck length squared, this is 1 over the Planck length squared. So we expect gravity to be just as strong as the electromagnetic force. So we expect this ratio to be 1 naively. Of course, we observe it to be, gravity is tremendously weak. It's 10 to the minus 34 or something. So this is the same, another way of posing this question is, why is gravity so weak? But this is really, fundamentally, it's the same question as why is the Higgs light, and why are we not black holes? So it's all ways of just saying the same problem. Now, of course, the weakness of gravity is very important for all the structure around us. So we actually went through some of these. So it's really what sets these really big, large, diverse length scales, like the radius of a planet or the radius of an animal, is all related to gravity. Okay, the reason these things are so different is because this number, this gravitational strength, is so weak, so small. So it's important, for us, obviously, but also for just this basic picture of the universe having all this stuff in it at different length scales, that gravity is weak, and we really have no good explanation for that. So this problem also has a name. It's called the hierarchy problem, but we also talk about different ways of talking about it, but it's really, I think, that the cleanest way to think about it is, why is gravity so weak? Why are these scales so far apart? Okay, so just to wrap up here, so naively, again, these basic principles that have been so successful, quantum mechanics, space-time, would lead us naively to expect a picture to look like this. We have these 3 length scales, and they're all basically the same. There's the Planck scale, the Weak scale, and the scale of the universe. And what we observe is very different from this. We have huge splitting. So 10 to the minus 17. Here, this is 10 to the 44, 10 to the 17. So it's totally different from what we observe. And life here is bad. Okay, we can't be there. So it's good that we observe this, but we have no real feeling for it. Okay, now of course our theory can't account for this. We can say that we live here, but it does that with these totally implausible cancellations. So we have these parameters that are correct at 1 part in 120 or 1 part in 60 by effects that are totally unrelated. So you just say they just happen to be that. Okay, so this suggests that it's wrong, right? I mean, no one thinks that these implausible calculations are what's really going on. And so, but what got us into this mess is these basic principles of quantum mechanics and space-time. Okay, and so if we want an explanation that's not these implausible cancellations, it's really suggesting that we need a modification of quantum mechanics for space-time. Okay, that's how we can. It looks like that's the only way out to avoid fine-tuning. Now, of course, we think space-time is in trouble already because we can't go lower than this distance scale. But it's suggesting that it maybe needs to be modified already to just explain these lengths. So now we can try to get an estimate for what length scale do we expect there to be modifications. Okay, so we said just for the existence of the Planck scale, or just for the existence of space-time, we expect modifications at the Planck scale. But what about for these other problems? So I'll take the Higgs mass problem. So we saw that in the current theory that the Higgs mass that we measured, this is like 125, it has 2 pieces. So this would be like the diagram that's for the classical piece, the input to the theory, and this is the piece that's from these quantum mechanical vacuum fluctuations. So this number is about the weak scale. Okay, this number we think is the cutoff scale squared. And if we don't want to have fine-tuning, so if we don't want these numbers to have to cancel very, very accurately, right, you can say what this number should be, right? And so we can only avoid fine-tuning if this cutoff scale is about the weak scale, right? Because so if this was the Planck scale, then we need fine-tuning at one part in 60, right? These 2 need to agree to 60 decimal places. But of course, if it happens 1,000 times bigger than the weak scale, or 10,000 times bigger than the weak scale, it's still tremendously closer than the Planck scale, but you still need fine-tuning at a level of 1 part in a billion, or 1 part in a trillion, and that's not good either. That's also impossible. So the only way to avoid this fine-tuning that no one's happy with is if this cutoff is at the weak scale. So that means that I think I say it here. So we have to stop these vacuum fluctuations below about the weak scale. So of course, it's critically important that the vacuum fluctuations are present, and we know they're present above the weak scale. But if they're present below the weak scale, that immediately leads to problems. So we need in order to solve this, we need something that looks like there are vacuum fluctuations, then at some point they stop, and they're no longer present. Okay, and as we'll see next week, another way of, the mechanisms that we have to do this, to stop these vacuum fluctuations, all come into there being a new particle that interacts with the Higgs. So this is another reason why the Higgs is so special, because if there is a solution to this, it has to talk to the Higgs. And this particle has to be about the TeV. Okay? Again, there's a squiggle here. But in order to apply fine-tuning, we expect something else in the theory that is about the TeV. Now, of course, this is exactly where the LHC is probing. So this is one of the big reasons why the LHC is interesting, is because we think that it can help tell us what is stopping these vacuum fluctuations at smaller distances. Okay, so we expect modifications to basic physics coming in at this scale. Now, totally unrelated to this, many of you will have heard that there's something called dark matter. Okay, this is coming from the astronomical community. And basically the idea is that when we study large structures in the universe, like galaxies, you can infer how much mass must be in this thing by seeing how these stars move. Okay, and if you do that, you get, don't worry about the details here, but you measure something that's totally inconsistent with what you expect just from an estimate of how much mass is in the form of things that we know about, like protons, or basically atoms. Okay, and so they're very different. You get very different behavior, and the leading solution for this is to say that, well, there's a lot of matter in here that we're not accounting for. So there's a lot of matter that's not in the form of atoms, and this is what we call dark matter, and that can explain the state of very well, right? And so this was actually something, this sort of technique has been very successful in the past too. So this is how we discovered a lot of planets. If you study a known planet, you can see how it should behave in Newton's gravity, and we saw deviations to that. And you can take two approaches. You could say, well, gravity's modified, and that's why we're not seeing that. But what actually, and the other approach was, well, gravity is correct, but there's some mass that we're not accounting for that's perturbing that motion. And that's how we discovered a number of the outer planets. And we think that same mechanism is here as well, right? So there's now stars that we're trying to estimate their motion and velocity, and we're not accounting for all the matter. Okay, and as we'll see next week, one of the leading candidates for what this dark matter is, or what it's made of, and the most maximal explanation requires new physics at exactly this length scale. So exactly the length scale that we need to fix this other problem. So it expects new physics at this weak scale, so 10 to the minus 19. Totally unrelated. So we have evidence that's, here they don't care about, these astronomers don't care about vacuum fluctuations, they don't care about Higgs particles, right? But they see something that they don't understand, and it's pointing to new physics at exactly the same scale. Okay, so in 2 weeks we'll talk about what sort of physics what sort of extensions to space-time do we need to stop these vacuum fluctuations, and how it's related to this dark matter puzzle, and how we can actually try to see it at the LHC. Okay, so maybe we'll take a few questions. For people that came in late, there's the wrong handout this week, but I'll bring the correct handout, and the handout for all the other weeks actually at the next lecture.
So getting back to your original question, what is the limit on which to stop building cyclotrons, say in terms of TeV?
So the question was, what's the limit that we should stop building cyclotrons in terms of TeV energy scale? So I'll give you the answer in GeV. It's 10 to the 20 GeV. So it's 10 to the 17 TeV. So and we're at 10. Right. So in practice, it's not a limit. But we think there is. Of course, we would really love to have 10 to 17 because then we could understand this stuff.
So I'd like to ask a question about these hard limits you put on the we don't think of new creation, like the universe coming into being. So we think that there was something there before that we are just seeing now. Now go to the other end of the scale where you said it doesn't exist. And if I could put two protons so close together as to make a black hole, then I would think that if I could feed more things to it, it would just keep sucking them in because it is a black hole. And I don't think of that then as it ceases to exist. It's more like you said, no information can come out. It may be inaccessible to us, but it doesn't sound like saying the same thing as it doesn't exist.
Yeah. So okay. So I'll address both things. So the upper scale is. You're right. It's not a hard limit. It's getting bigger. As the universe gets older, we're able to see farther and farther out. We think that there's stuff out there, right? But we're just not able to see it yet, right? And so that upper limit will get, it will get bigger, but it's getting bigger linearly. The scale is a log scale. So in terms of within factors of 10, within our lifetime, there's no change. Okay, and within okay, so that's one, and it's not going to be dramatically bigger. I mean, it's okay, but it will drift a bit. Now the lower end, right? So you put two protons close enough together, you make a black hole. But you say, okay, maybe there is space-time at even smaller distances. You can go on thinking that there is space-time at smaller distances, but you'll have no way of knowing it, even in principle. There's no way of accessing what's happening at those things. You could pretend it's still there. But operationally or experimentally, there's no way, even in principle, to deal with it. And every time that this has happened in physics, it's taught us that notion it makes no sense to think of the notion. Right? So you can think of that, actually there is position and momentum that you can know arbitrarily precisely, or it is there in principle, but you just can't know it arbitrarily precisely.
Well, what do you say happens to the things that fall into the black hole then? They stop existing?
So we think that
nothing. Basically, is what it sounds like.
Well, I mean, being within the black hole is very different from being outside. So when you're in the black hole, when you fall in, it's probably okay at first. I mean, we don't understand. Okay, we don't understand in detail yet. But the current thinking is, in the current theory, there's a singularity at the center of the black hole, and that's something that's going to infinity. So no one believes that that's what's happening. There has to be new, because that's exactly what the Planck length is. So there's likely new physics that we need to understand at these very, very small scales, so quantum gravity, that would explain what's happening. So until we have an explanation for that, we don't know what happens when someone falls into the black hole, according to the person that's falling in. According to the outside, they just disappear, essentially. Or they actually slowed it. They stop. So then there's questions about information that I'm not going to get into because I'm not an expert and that's heated debate. So, but in terms of our practical purposes, there's, if someone comes up with a theory that's much, much smaller than the Planck scale, it can never be tested. So maybe it's correct, maybe it's not correct, but even in principle, it can never be tested.
One thing we never covered here is time. So what's your thought, or what's your current thought, on time being quantized like chronon?
Right. So we've covered time because remember, this is the big lesson of lecture 4. There's no units, right? There's only, everything's dimensionless number. So you can I could have made the exact same plot in terms of time by multiplying by the speed of light. And so that's saying that there's no times smaller than 10 to the minus 43 seconds, which is little, right? Now, and then another question was, what about this being quantized? So a very naive thing is, okay, yeah, space-time doesn't exist below the Planck length, but at that point there's atoms of space-time or something. It becomes a lattice or something. And that you can show is not correct. You could show, one thing is the size of the lattice depends on how you're moving, so you don't expect there to be the principle of relativity to be satisfied. So we think that's not the way that it happens. And we actually have we have some ideas for what kind of things are happening, and they're all associated with the boundaries. So some of these are. see how should I say this? So we have toy models where you can describe a theory that has gravity on the inside. It's with the exact, in the exact same way, just by the boundary. Okay, so just by what's happening, it's a different theory, but what's happening on the boundary. So this is something that would actually be good to get a lecture, Compton lecture on. It's called, it often goes by the name of ADS-CFT correspondence or principle, but it's also the holographic principle. And so the notion is, in these theories, a theory that has gravity and it has one extra space-time dimension is exactly identical to a theory that only lives on the boundary. Okay? And so that's suggesting that the notion of space, or in that theory, you don't need the space. Right? You can explain everything just by the boundary. And so we have other suggestions that something like that is happening. So, for instance, with black holes, if you can ask how much information is in a black hole, it goes like the area of the black hole, which is very strange because normally information goes like the volume. So if you wanted the information in this room, it would go like the volume of the room. But with black holes, black holes have massively more information than the equivalent area that's not a black hole. It looks like almost all the area can be encoded just on the boundary. Okay, so and so that's also very strange. You wouldn't naively expect that. But that's also suggesting that maybe the inside doesn't make sense or isn't necessary. And then the third thing that is maybe depends on again, it depends on who's talking about this, but you can ask what quantities does quantum mechanics predict even in principle? Okay, so there's these. I mentioned that things are probabilistic, so it only predicts probabilities. So that suggests that you have to do an experiment infinite amount of times to get arbitrarily sharp prediction. But actually, another thing that can happen, I didn't really harp on that much, is that the measuring device that you're using is also quantum mechanical. Okay, and there's an incredibly tiny but non-zero probability that thing just screws up. Okay, so it has some probability for just breaking, right? And that probability, and so that would introduce an uncertainty as well, which is again totally relevant for what we deal with. But in principle, that uncertainty is there, and if you want to make that uncertainty small, or if you want to minimize that uncertainty, you make the device bigger. So you make the thing you're using bigger, and so you can say, all right, well, let's say I want to measure the temperature in this room. I'll make my thermometer bigger and bigger and bigger, and this uncertainty will get smaller and smaller and smaller. Of course, you make the thermometer big enough, then you make a black hole, right? And so now it looks like there's a thing. So even in theory, quantum mechanics can't predict arbitrarily precise local things, right? There's some inherent uncertainty because of black holes. So what you could do is you could make the thing infinitely big. Right, so if you make it infinitely big, then you can have infinite mass, and it's not a black hole because it's not close together. And that's kind of like what we're doing at the LHC. So in this thing, you could have an infinite thing here, an infinite thing here. You shoot up something at each other. There's some probability for that to interact. It comes out, and that can be measured arbitrarily precisely because these things can be infinitely big. You could do it infinitely often. And so again, all the action there is not is in the middle. Right? It's suggesting that even the things that in principle the theory can predict are only associated with the boundary. And so a lot of the ideas that talk about what happens when space-time is replaced are taking the notion of space-time and moving it to some boundary condition. And so which is much more radical than just being some notion of an atom or a lattice of space. But you guys should definitely ask for lectures on this.
You indicated that there's a singularity in the black hole. What is the difference between that singularity and the singularity that created the universe?
Right, so the question was about singularities for black holes. There's singularity within a black hole, I said, and what's the difference between that and what's the difference between the singularity that created the universe? So, I'm not the guy to answer about the differences. I'll tell you what's the same about them. What's the same about them is that people believe that we don't understand well either of them. Right? So we don't think that the singularities are real. We think that that at some point a new description of physics comes in and it removes the singularity. So there's something, and the singularity is saying that everything is infinite, right? And so we don't think that that's happening. It's really that the logic is breaking down. And so we think that the logic will continue to be consistent, but we're just using the wrong theory. Yeah, I mean, I'm sure there are differences between the two, but you should get somebody else to go through those.
But it doesn't matter how nice or beautiful a theory is, unless you can verify experimentally.
Right.
It's still just hypothesis.
Yeah, right. So that's why. Right. So the comment was, doesn't matter how beautiful a theory is, it matters if you can verify it. I totally agree with that, and I think that's why people are happy to get rid of space-time at the small scales, because there's no way operationally of verifying any theory that happens there. And another thing that I want to say is that the whole theory that we have, it's not like we've chosen it because it's beautiful. I mean, it actually is beautiful. The math behind it is very elegant and beautiful, but that's not the reason we chose it. We chose it because that's the only way that we could get things to be consistent with these basic principles. So it's true that there is beauty to it, but it's also the case that we really had no other choice, which really makes you think that we're onto the right thing. When you have no choice in what you're doing looks correct. It also looks very beautiful. It gives us confidence that we're on the right track. And it also, by the way, predicts things that we then find 60 years later. Well, do better.
When you showed the graph of gravity being constant down to a certain level, and then suddenly it veered upwards, you were describing the force between two protons.
Right.
So there's a electromagnetic force involved there. Why didn't you select two neutral particles?
Right. Yeah. I mean, I could have done neutral particles, but then the denominator would have been 0. Right. Then there would be no force between neutral. I mean, that if you ask what if you really want to tell us how big is a gravitational interaction with respect to another interaction, you could choose. It's infinitely big compared to neutral things, but that doesn't really tell you much about the strength of the gravitational interaction. It just tells you that these particles have no electromagnetic interaction. But I could have chosen, we would have got a different number if we would have picked electrons, right? Then their mass is smaller, and instead of 10 to the 34, it would be like 10 to the 38 or something. But the point is, gravity. I think it's really it's a qualitative thing. Gravity is incredibly weak, totally irrelevant at large scales. At these very tiny scales that we've never been to, it starts getting bigger, and then it starts dominating. And when gravity dominates, then you get into trouble because you can make these black holes. So that's really the takeaway. I mean, another thing is, force is a derived thing. So really you should think of this. We measure the interaction strengths in cross sections. So I didn't want to go into that, but it's the exact same logic. That you can measure the cross section, the gravitational cross section at large distances, totally irrelevant. It starts getting larger, and then it dominates, and then you get black holes. So you think of it as a qualitative thing, but there are calculations behind it.
If the graviton exists, what do they estimate its energy range would be like they did with Higgs? Can they
It's 0. It's 0.
It would be 0?
Yeah. Okay, so maybe we'll end there. If you have other questions, then I'm happy to answer them. And then no lecture next week. And then the week after, we'll try to give some suggestions about what can get us out of this mess and how we can test it.